There is one more equation in projectile motion I want to derive that's going to help you with problems where there's not a lot of information given, which usually means it's not so easy to solve. So the more information given, the more things you have to plug into an equation and solve the problem. So anyway, this is going to be the range equation. And the range equation is going to enable us to do, again, difficult problem types easily, where that would normally take a couple of equations to solve. Well, we're going to solve this equation with a couple of previously known expressions. And that will kind of do the upfront work, and you can use that to your advantage going forward. So the question is how far does something travel along the ground, the range, given an initial speed? So I got a speed. What's the maximum range for a projectile? That'd be a good question to ask. It doesn't just pop out very easily. Well, let's analyze this, and we'll get a result that will be quite useful. So we know that range is Vx times the flight time. That's really the answer right there. I mean, range is horizontal motion times the time during which that motion is taking place, which is the flight time. So that's the answer. But typically you may not know Vx or the time. All right, so in fact in this case we don't. So we're going to solve for this in a way that gives us just a small set of variables, including the speed of the object. So we want to maximize. What do we want to maximize here? If we want the range to be maximum, and I'm using that as an example because the equation I'm looking for that I want to arrive at will emerge from solving for the maximum range. Now you have an intuition already. Given a certain speed, what angle do I need to launch this to make it go the furthest? I know what you're thinking, but it's just a guess, okay? And so your guess may be correct, but let's see. All right, so in order to make it go the furthest, given it a certain speed, you can't adjust the speed, it's V0, whatever it is. You want to maximize the amount of this that's horizontal, because that's what makes it go along the ground. The vertical part of V0 does not move you along the ground. However, the vertical part gives you more time of flight. So the problem is this. We want to maximize the horizontal velocity, and you want to maximize the time of flight. But to maximize the horizontal velocity, you have to point it horizontally. To maximize the time of flight, you project it vertically. Those are opposing requirements. Because how much time is a projectile in the air if we direct it completely horizontally? Well, if it's along the ground, that'd be 0. Maybe it's up a little bit, but in any case, in other words, up off the ground a little. However, this is looking at same elevation, beginning and end in this particular problem. In any case, it minimizes the time if you project it horizontally. To maximize the time, we would direct the speed vertically, right? Straight up. But then what's the horizontal speed? The horizontal speed would be 0. So the range is 0. Doesn't matter how long it's in the air. Didn't go anywhere. All right, so you see the tension we're going to wrestle with here. So let's obtain an expression for the time of flight. Here's our answer still. Let's get time of flight. I'm going to use equation 5. The beginning and end are both 0. Y 0 and y are 0. So we get the simplified form. A t goes away, and we get the expression for time up and down is 2vy0 over g. Now, the time up and down actually is 2 vy0 is v0 sine of theta over g. So we're now ready to plug that time into our expression for the range, vx time up and down. So let's do it. But what's vx? Vx is the initial speed cosine of the angle. So now range is Vx, here it is, V0 cosine of theta, 0, initial angle, that's Vx. Time up and down is this, so we'll put that in there. There it is. That's our answer. Well, let's work with this a little bit. That's 2 v0 times v0 is v0 squared, sine times cosine over g. Well, that's a little bit cumbersome. So we're going to simplify that because having had trig, likely, you might know or might recognize that there's a trig identity that will simplify this for us. So what might be familiar to you is the trig identity. Cosine of theta sine of theta is 1/2 sine of 2 theta. Double angle formula, right? So we can put this together now and express the range v0 squared sine of 2 theta over g, theta 0. This is all initial conditions, right? Initial speed, initial angle. All right, so that's a powerful little expression, but make sure you recognize it's only valid for this type of motion. Beginning and ending positions the same. Not to an elevation, nor from an elevation. That's different, okay? So, there it is. Now, we still haven't answered the question, have we? The maximum range then will occur when this thing is maximized for a given speed, a given g, namely the surface of the Earth, probably 9.8 meters per second squared. So we're going to be able to adjust this to maximize it. Well, the biggest this can be is sine of 2 theta 0 is 1, right? Sine of 2 theta 0 equals 1. That occurs when the angle, namely 2 theta 0, is 90 degrees. So it does match your intuition, doesn't it? The maximum range occurs when the initial angle is 45 degrees. Note, however, I will say in passing at least, that this is only true without air friction. When you include air resistance, the practical reality, if you want to hit a baseball the farthest, you're not going to hit it at 45-degree angle. You're going to hit it at an angle somewhat less than that. So the air friction is, when it's included, is certainly going to reduce the range. And the way it works out is you want to plow more directly into it. So it's a little bit hard to specify, though, exactly what angle that is. It changes based on the conditions of the air itself and the geometry of the object, etc. So let's anyway do a example problem now. So what's the muzzle velocity of a rifle if the bullet hits a target 1,000 meters away when it's only launched 2 degrees above the horizontal? So how fast do you have to launch it? So 2 degrees, hits the target 1,000 meters away. Well, you could do that without this equation, but it takes some head scratching. But now we have the range, v0 squared sine of 2 theta over g, and we can solve for v0, square root of rg over sine of 2 theta 0. Now just plug in the values. 1,000 is the range, g is 9.8, 2 theta 0 is 4 degrees. And that gives you 375 meters per second. So that was nice, it was easy to do, and you can put that in your arsenal of projectile motion equations from now on. Well, that will conclude our analysis of projectile motion problems. You have all the equations you need to solve any problem. Trust me, you do. At least the ones I'll be asking you to solve. Oh, this is kind of interesting. They're actually including, in this range expression we just found, an initial height. Don't think too hard about this, or you will lose out on the real important things in life, like winning. Okay, we'll see you at a later time.